So, action 11. Okay. And so today we're going to look into the correlation function in mean field approximation. And then we're going to start with the Landau-Ginzburg. Theory, formal, and heuristic phenomenological. It's called phenomenological. And then the Landau-Ginzburg will keep us busy for the next week, at least. Okay, so let's get started with the first topic on the correlation function in field approximation. So the last Tuesday, we calculated a lot of critical exponents, which told us the behavior around the critical temperature, how certain response functions of the system change there. And what we were missing was the correlation function. And so the correlation function, in fact, is it's a little ill-defined in mean field theory, right? Because what you do is that you describe the field of your neighbors by the average of the whole field. So you basically throw away all correlations. And yet still we want to calculate the correlation function. And so the trick is in the end to not throw away all correlations, but keep some to first order. So remember, the idea of mean field is to discard fluctuations around the average magnetization as small. So that means if I look at the product of two spins located at position I and J, I can write this, and here I'm just expanding by the average of SI plus the average of SI minus the average of the I's plus the average of SI. And I do the same for SJ. And this allows me to write this as the product of the fluctuations around the mean and the product of the means. So I have SI 0 times SJ 0 plus, and then higher order, SI 0 times SJ minus SJ 0. Sorry, let me actually, sorry, I need to write this in different form. So I want to split up individual the fluctuations. So this is the fluctuations of I, and I'm multiplying them. So I have this times this is this term. Now I'm taking this times this. That's J0. And now I'm taking the product of this times this. So that's then SJ minus 0 times SI 0. And now I'm missing the product of those two. Okay, so we found out a way of writing a product of two values as a very long expression. Sure, I do, I agree. But it's very meaningful because now we wrote down the product of the two spins as the product of the mean and the fluctuations. And the way it's written here is that we're here looking in linear order at the fluctuations of spin I, it's the average, linear order of fluctuations of spin J, average, and then second order of both of the fluctuations. And so if I follow the mean field ansatz, I would say these fluctuations are small. And even to second order, that is very small. So that means that if I now were to take the average of Si and Sj, this is just the product of the averages of itself. And so there's no correlations. Okay. And that's tricky because we want to determine the correlation functions, right? So how to derive approximation to the correlation function from the mean field approximation. And so the trick is to use a local version of the response dissipation, fluctuation response theory. So fluctuation response theory, which says that our xi, sorry, that's meant to become an xi, ij, which is defined as beta n sum over the correlations, is 1 over n kbt si sj minus si sj is nothing else than the derivative of the magnetization. So si with respect to, and now I give my magnetic field an index j. So what I mean with a local version of the fluctuation response theorem is that I, for the purpose of this derivation, assume that my applied magnetic field H is varies for every individual spin. So now my applied field gets an index J, and that allows me to write my response directly then also as derivative of the partition function. Then it's the second order derivative of the free energy. Here I'm using the partition function, ln of the partition function, dhi dhg. Also note this down where we here assumed field H I can varied independently Okay. Okay, so now we're going to do a mean field equation with this local applied field. And so what we're going to do, because we realized that this answer here was a little too strong, is that we're only going to neglect the second order fluctuations, and we'll drag along the first order fluctuations. And so why did we look at the SISJ? Well, it's the correlations, but it also turns out, like, if you look at the interaction Hamiltonian, it's precisely what enters in the Hamiltonian. So we can directly enter this result into the definition of our Hamiltonian, hence our partition function, to then here derive the correlation. So we now take SISJ as SI average, SJ average, and now we consider the fluctuations in linear order around the mean. Neglecting and so if we now, like, I know we did a long exercise to write a very short term and lots of terms, but now that we actually want to put them into action, we can simplify this again, because we realize that actually the product of those two and the product of those two are the same, and they're identical to these terms. So what we in fact have is a minus SI SJ plus SI SJ0 SJ SI0. And now I'm going to use this for our Hamiltonian, where we're looking at the interaction minus, and now note the HI travels into our applied field here because it's an individual property of the spin. And we need this to successfully take these derivatives here. Okay, then our mean field partition function becomes, indicate this field, sum over all states of spins, e to the beta j, and then some ij. And now I'm entering this expression in here. So we get minus SI0 J0 plus SI0, and the second term, which is minus minus plus. Yep. This first term is independent, like this doesn't differ as a sum over the states because it only has the averages in it itself. So I can pull this prefactor out. So that's better J sum ij to minus si 0 j 0, and then here's summing over states. So what's left is then Si Sj0 plus Sj Si average 0. And this I can actually the indexes I and J are interchangeable, so I can simplify this as the sum over 2 beta J Si average Sj. Like this one. And then we may realize that actually sorry. Actually, this is a sum over the SI, pops up both in the later and in the further, the first term and the second term. So I can rewrite this one more time as E2 now, sum over SI, and I pull out the SI, and then I have a sum over the J's that are neighboring SI left, SJ 0 plus beta HI. Oh, sorry, it's different. And so this is now the form that we used to have before, right? So now we have here quantities that are such that I can sum over the different states, putting SI to +1 and -1. And that gives us the cosine hyperbolicas that we had lots of times before. So now the partition function for this terms results into beta J. And now I'm summing over J neighbors to I as J plus, oh, sorry, I had pulled out the beta. So it should be here anymore. HI. So this is analogous to the derivation of the partition function we had before, except that now we're dragging an index with the h, and here we're summing over the nearest neighbors of I. And then we have the partition function, so we can actually directly write down the free energy per spin. Yeah, and free energy per spin, I'll always give the small f, free field, sorry. Yes.
Right now, 2 and okay, I think.
Sorry, the 2, so what did I do with the 2? The 2 I dragged out, and then I so I dragged out the 2, but the 2 should be gone again because, sorry for that. Okay, so wait, here the 2 is correct, but yeah. What I'm doing actually when I go from this line to this line is that I'm dragging out the sum over SIs, and so what I'm summing over when I sum over SI and SJ is actually I'm summing over the amount of bonds, right? But if I drag out the sum over summing over the individual spins, then I count the bonds twice out of a sudden. And so to get rid of this counting twice, I should normalize and get the 2 out of it again. And then this makes sense that this, also comes in linearly. So this makes, and then it's really like writing down SI, like writing this again as a product of the individual spins SI, putting in then the spins are +1 and -1s, which gives me this cosine hyperbolic, and then this is the products of these states again.
But another thing that I'm wondering about is this sense theory, like the potential function.
Yeah.
Is this already basically skipping the procedure of minimizing the like a parameter by just making this answers? Or is it like a different field?
So we gonna we still know what so we're still deriving the free energy and we still need to minimize it later.
Oh, okay.
So it's just so the reason why you're seeing this again is that we now introduce this individual magnetic field.
Okay.
But that's it. I know in a sense I'm showing exactly the same that showed either on Tuesday or last Friday, except for this one. So we're really calculating the free energy yet again, and then we have to minimize it.
Okay.
I'm gonna leave out a few steps in between, like here, because it's exactly the same. So the free energy per spin is then,
Sorry.
yeah.
Why do we restrict ourselves to nearest neighbors? Because so far,
because we are only looking at nearest neighbors Ising models from the setting. So the sum of this Hamiltonian here, this was always the interaction strength is only for those spins that are nearest neighbors. And it's, I think, only on problem sets that you actually see other longer range correlations, which may have happened to you. Yeah. Okay, that's the log of the mean field partition function. And so I agree that like a better formal notation would be to treat this as this phi. Yeah. Anyway, okay, so if you take the log of this function, we arrive at this is from this term, right? If you take the log of the exponential, we get a linear term. That is the beta cancels j over n sum over ij s I s j. And then the second term, we keep that we take the logarithm of 2 cos h. Sorry, let me try to close all this. Yeah, I think. And so this would be actually our like capital phi potential that we need to minimize to find the optimal free energy. So minimizing the free energy now with respect to hi then leads to and that follows analogously as I guess last week as j, sorry, 0 plus hi. So it's the analogous condition for the optimal mean field, defining the magnetization with now here the applied magnetic field having an index I, and also note that this looks slightly different, right? Because now we here have the summation explicitly stated. And just if you sit down and want to do this derivation right yourself, which I'm omitting here because I think it doesn't add to see it just again, if you take the sum, sorry, over a delta function like this, which you get when taking the derivative, this gives you delta ik. And also if you do the sk0 with respect to such a summation, si, you get which is then equivalent to writing this, oops. You need these, you will use these identities. Okay. What is important for us is that we found this condition, and now we do the same kind of thing, that we want to, we're troubled by this being an implicit condition on the spins themselves, and we want to take the derivative of the spin with respect to the applied field, right? This is here. This is what we're aiming for. But we only have the magnetization given in an implicit form. So what we do is we expand this expression yet again for small magnetization. So around the critical point. So we're interested, oops, wrong color. In critical region. Magnetization is small. And so we use this to expand H. And that gives us then minus beta J neighbors of I as J0 plus as I0 is equal beta H. And now we want to solve this for the magnetization, but we have the challenge here that we're having the average spin of Si and the summation of the average spins over the neighbors of I. We have these terms. I mean, just to make sure that you understand why do we now have to deal with this stupid sum that we didn't have to deal with on like in the last lectures. The reason is that to first order approximation, I'm throwing away these fluctuations, right? So this term arises from us taking these higher order terms into account. And what we did so far in the last lectures is we only considered those. And that's why this term didn't bother us. But now it bothers us, right? Because now we have to take into account that there are some fluctuations in my neighborhood. And so I have to sum over the average spins in the neighborhood of a spin I. And neighborhood means that I'm actually looking at the Brillouin zone of on my lattice of my spin, and I want to sum over the states. And so how I deal with averages in my Brillouin zone is that I often go to the Fourier space. So I take here now a discrete Fourier transform. You saw a version of this very early on in class, I think in the second lecture when we did the phonons as an example of field theories. There we also, used Fourier transforms to learn about our systems. Where we now define SK as the sum over our lattices plus minus e to the I k r s. I'm sorry, this doesn't need to be up there. sj. There we go. And so we assume a lattice with unit vectors e mu and neighbor sides plus minus a e mu. And then so if we now take the Fourier transform and we go into these neighboring states, we realize that we can write this as Ka times A, the wave vector in these unit vectors that are spanning my lattices. And in principle, I can have neighbors to the left and to the right. That's why I have the plus sign and the minus sign. And if I lump this in and sum over plus and minus, I get a change of sign here that gives me then e to the plus I ka plus e to the minus I ka. So I get a cosine from this contribution, so that this equation above there now becomes minus beta j sk summing over now just a along one direction of the lattice cos ka plus sk, and that's then beta, and hk is accordingly the Fourier transform of the applied field. And now this equation I can solve for sk, and that gives me 1 minus kbt minus j sum over a 2 cos ka times hk. And so now that we've solved it, we can put it back into the back Fourier transform. Sorry, and I should have, it's not really consistent. So I'm summing over now the Fourier zone, and actually, I think it, yeah, we can just make this an integral too. BDK PID. And we already see that this expression is divergent when this term becomes 0, which happens when we're at the critical temperature. Let me show this. This. So T is equal to TC that we had already identified. Because if we now look at this expression here, sorry, there's a 2. Okay. And I expand this term, then I find I have J over the coordination number as the first term, and then Ka squared plus higher order terms, and that reads nothing else than taking this knowledge of how the critical temperature is defined, we can write this as KBTC plus J sum over all KAs quadratically and so on. And so these two terms cancel at the critical temperature. Okay. So we're happy that we recover our critical behavior, and now we finally turn to calculate the susceptibility to arrive at the correlations by taking the derivative of this magnetization with respect to the applied field within index K. So so this we had defined, if I just copy this down as dSi dHj, and now we can formally do this and find and here moved out the T to define the reduced temperature again, right? T minus Tc over Tc. Because we saw that here the first order term has the critical temperature in it, so we can just write this then as a function as 1 plus 1 over z sum a to 1 minus plus. Okay. So just rewriting so that we have the reduced temperature here and a term that should vanish at criticality. And so in principle, we have here now a result that we can define for any lattice, and we can sum over the Briand zone. We're interested in general results, and so what we're interested is the long range correlation, so at large distances, and so that would be looking at the following expansion at large R's. We have only small k, and then we have this becomes 1 over Tc. E minus R k, and we only need the quadratic contribution, and this is well an integral we can solve, or let's put it that way, it's an integral that we once gave a name to, namely this gives the Bessel function that I defined like no, sorry, that's a T. Whoops. TR. But the cool thing is that we know a lot about the Bessel function, and particularly its scaling for large values. So we actually know that at large distances, this goes roughly like 1 over Tc. Just copying down the prefactors. And this is square root of the argument T over R E minus square root TR. And that's, so we can read off our correlation has an exponential decay. And remember, we defined the correlation length as the length scale over which our correlations decay. And so this is now written in here, so we can read off the correlation lengths. C is T minus half. And so the correlation length was defined via the critical exponent nu. So T minus nu. So we can read out that here in this case, nu is a quarter. And we found another critical exponent. Yay! Note that this is really the behavior as we approach criticality. At criticality, we expect this power law behavior, right? The scale-free behavior that we, like I gave an argument for on Tuesday. What does it mean to be scale-free? Scale-free means that an exponential function is not scale-free because if I map ranges, they map onto different ranges. But if I have a power law, which means like a function to any exponent, like x to any exponent, then this is indeed scale-free, and behavior at one order of magnitude, another order of magnitude can be superimposed by just a simple rescale. And so at criticality, we especially expect this this power law behavior. And so in this, at criticality, the following that exactly at the critical point. So at small t equals 0, right? Then I have a different integral here. And if I evaluate that, I find that my correlation is then 1 over r d minus 2, which is, again, if we use the definition of the critical exponents, the definition was r d minus 2 plus eta. So we find that eta mean field is 0. Okay. And so, yay, we given that we started out being very unsatisfied at only being able to exactly solve one-dimensional systems where we don't have a phase separation and series expansion, leading us to at least find the critical temperature, but not any critical exponents. Mean field theory, albeit its limitations, gave us a chance to actually really calculate the behavior at criticality and derive critical exponents. But it's an approximative method, and we are aware of that. And so what we do? If I find, okay, this is something that I can derive analytically, but how good is it, or in which particular regards is it good? What I do is I try to compare this to numerical simulations. And so this we can do here, and I just want to give you the comparison on, yes, okay. So to give you a summary, the mean yield critical exponents. Okay, so this is the critical temperature. We're interested in alpha, in beta, gamma, delta, eta, and nu. And we're going to compare the mean field theory to d equal 2, which, as I said, like I'm not going to drive you through the ordeal of how you can, like in a very complicated manner, calculate exact results, but we do have them exact results, so let's compare to them. And d equal 3, in 3 dimensions, we look at numerical results of these exponents. So this is 1. Here we saw a jump in a specific heat. This was a half, 1, 3, 0, and a half. And in d equal 2, we have 0.57. We have, sorry, t over tc. So it's absolute values. 5, 1.75, 15, 0.25, 1. doesn't look that great. Okay, but we knew that like mean field approximation is better the higher the dimension, right? So the higher the amount of the coordinate the lattice sides that are mentioned. So let's keep our hopes up for d equal 3. And so there we find numerically and here there are, and I'm sparing these, there are error bars in principle to all these values. 5, oh gosh. Okay, and now you see why it was strategically a good idea to first show you the results for d equal 2, because they are like way off. And then if we go to d equal 3, you see like we're still off, but not as badly off. So like really our intuition that as we go to higher dimension, mean field becomes a better and better approximation is indeed true. And you see like, you know, okay, so this was like a factor of 2 off, and it's much less off. Here we're much less off. This is approximating each other. This is, you know, reasonably well. Okay, the jump doesn't work out, but also for the critical temperature, we're getting close. So it's an approximative method, but given its simplicity in the amount of writing down that you need to do, it's actually quite powerful, because we actually recover qualitatively the behavior, at least in higher dimensions, correctly, and also the critical exponents describing the behavior is putting us in the right field. But obviously the bottom line is that we need better methods. And before we finally, yes.
Have we at least predicted the critical temperature wrong, or is it also different?
Well, you know, it's 0.75, right? So,
oh, it's good. Okay, nice.
Yeah, but you know, it's not as, yeah, it's, yeah.
Yeah.
So yeah, no. The answer is no. But yeah. Okay, so but before we you know actually finally arrive at renormalization group theory, which is the best method that we have, let me introduce to you first the Landau-Ginzburg theory, which is kind of the formal ground of mean field theory. You can see it as the formalism that's also behind mean field theory. Mean field theory sort of like is for me like this easily motivated approach, how you realize that this is a description of the dynamics of an interacting system. And now Landau-Ginzburg really provides the formal ground of like how can we generally write down field theories in a formal way for any interacting system without you know, this kind of lucky choice for the Ising model that we have this interaction term and we have this applied field, and we can, you know, approximate nicely the full Hamiltonian of the Ising model with this paramagnet, right? I mean, that's kind of sounds like a lucky coincidence, but then Landau-Ginzburg will show you that there's actually this is well rooted in physics, and there's a formalism of how you can actually write down approximative Hamiltonians and look at the dynamics of any systems. And so that's now Landau-Ginzburg theory. And like, even if your heart is not on statistical physics, but condensed matter system, like, you know, this is very fundamental physics. And here we're following Carter chapter 2, and sometimes Schwaben, chapter 7.4. Okay. So this is now like the former setting of the refresher that we had as a motivation in the second class already, looking at phonons, right? Remember when we looked at the phonons, we said, okay, phonons in these are all my my atoms making up my material, and they're vibrating, and I can count their vibrations and look at the dispersion relation. But just looking, describing the individual motion of all particles gets pretty cumbersome if you go to higher than one dimension. Yet again, right, like we can only solve one dimensions all the time. But what I can actually do is I can look at these vibrations by making a field theoretic approach of saying, like, actually I coarse grain, I don't look at the individual atoms and the atom spacing, but I'm averaging over a spatial, I'm coarse graining to a spatial size that's much bigger than the individual lattice spacing, and then I can just describe the dynamics of these phonons as a field that is slowly varying in space. And this is actually a really adequate description, because what my phonons are doing is collective dynamics on long wavelengths, and sort of actually the lattice spacing doesn't matter to describe these long range collective motions, and a field theoretic approach by averaging over a whole set of individual particles is very powerful, because all of a sudden I can not only solve 1D but also 2-dimensional, 3-dimensional systems. And that's again essentially the essence of the idea of Landau-Ginzburg theory. So the idea is okay, so and phonons don't have phase transitions or critical behavior, but I think they nicely establish the idea. And now we're really interested in describing systems that do show critical behavior. But again, as we know, at criticality, we have these long-range correlations. So that we should be successful in describing if we average over, if a coarse grain over the lattice spacing. So critical behavior coincides with long wavelength correlations that are much bigger than the lattice spacing A. And so I can coarse grain over the microscopic properties on scale of the lattice spacing to describe the dynamics as a function of a continuum variable. And that's the start of the statistical theory. And if we now turn to our beloved case of magnetic systems, I mean, just make, so, we're already kind of coarse graining, and when we say, like, we describe our individual atoms as spins, right? I mean, the magnetism really originates from, in the end, quantum mechanical properties of our atoms and the electrons circling around them, and really, if you want to do a very, very exact job,
then we would really need to write down even a Hamiltonian that's really representing the quantum mechanical and electromagnetic nature of this whole setup. So now we're not staring at a Hamiltonian that's as nice as an Ising model, but it's like, you know, the whole long functional thing. So this would be the accurate starting point to describe the system, and obviously we don't want to go there, right? But I mean, just to remind us that this is actually what we're in for, in principle, if it wasn't for like the approach of statistical field theory. So for a magnetic system, magnetism originates from quantum mechanical behavior of electrons whose overall thermodynamic undefined so in principle I have this Hamiltonian that really takes care of all the electrons inside. So I have a microscopic Hamiltonian accounting for electrons. And so now it's very obvious that this is impossible to calculate. So and so the idea instead is to describe find a continuum variable that describes nicely the state of the system. And here we already learned from our mean field theory approach that we found an order parameter. Remember, we found that the magnetization is actually a very good order parameter of our system because it's different in the different phases. So that's a physical intuition that we gain looking at a system that didn't give tremendously great results, but we learned something in the process, right? So we know that magnetization is a good order parameter to describe our system. And so now magnetization may very well be a very nice continuum variable to describe the states of a system, of a magnetic system. So we define a magnetization field. M of X, which is representing now the average over the coarse-grained spatial regions of elemental individual spins. And the average in the vicinity of my spatial coordinate X. And so now X is a continuous variable. But this is not only a valid description for any wavelength changes in the magnetization being much bigger than the lattice side. Right? So as soon as we arrive at variations that are changing on the order of the lattice spacing A, we know that we can't trust these results anymore, right? So we should always keep in mind that this is an approximation that we make in the beginning, and so that whatever result we arrive at, we should check. And so in a formal way, I can now write down that I want to describe these microscopic partition function in terms of my order parameter, hence my magnetization field, where I'm kind of summing over the microscopic Hamiltonian in coarse graining out the magnetization. And so just formally, I can preserve the partition function and write z of t, which is defined as by the microscopic Hamiltonian of the system as t So I'm again summing over all states, which means that I'm integrating over all field configurations weight by the sum, the weight, counting them by the individual weight. Weighted weight. So I basically wrote down, the definition of the partition functions now in terms of fields, or field configurations, field states, and their associated like W, which is kind of representing the Boltzmann effect. And so now, in principle, I can think about doing this in a formal way, sort of bottom up, starting with my my spin systems and averaging this to arrive at to derive what is my W for my spin system. And so the formal approach to determine W, which I would call, that's the sort of bottom up. You have this a lot if you want to describe complex system, any complex system, and that's kind of what I do in my everyday life. I try to describe biological systems, which are inherently complex, and we don't have yet the physics to describe them. And so there, I have a choice on how I can approach, like trying to understand the physics of the system. And one is to be bottom up, and the other one would be top down. And bottom up is really always the idea. I know the physics of the ingredients, and I write them down, like in the full plethora and then nastiness of like being very, very lots of terms, and then I try to coarse grain and and simplify and argue why I can neglect certain contributions and so on, to then arrive at a system that I can solve or make statements about and understand the system. And the inverse, which I hope we get to today as well, is also that I can start top down and say something about, oh, actually, I know symmetries of the system, so I can firsthand write down like that this system should be described by a set of these sets of equations, and I will study this system. Like, for example, in biological physics, a very well-trotted approach is to assume that our living entities are optimized by evolution, So everything that we see now on Earth is there because it prevailed in millions of years of evolutionary competition. And so it should be optimized for function. So I can sort of start like saying like, oh, you know, my system is should be caring about like being very efficient in its use of energy. So that's my optimization principle. And that would be like a top-down approach. I state this clearly, and then following this principle, I can derive equations that describe my system. And so here is an example where we can see these two approaches in the context of statistical field theory. So we can define the continuum magnetization and here, just to give the example, I'm going to confine myself to a one-dimensional system again. So what this continuum variable actually means is, sorry, and since it's 1D, it doesn't have a vector, sorry, oops. Okay, let me track. So I'm summing over the volume of the system. I know D is equal 1, but let me state this here. And I'm averaging over a number of lattice points, lattice sites that have individual spin SL, and I'm going to apply a coarse graining function. It's coarse graining about the individual lattice sites located at XL to then arrive at a magnetization as a continuum variable. And so this function g of x, for example, could be the following as is a normalized coarse graining function. And so it could, for example, look like that. You know, I have a kernel over which I'm moving over my lattice and I'm integrating all that. What is important is that the lattice spacing A is much smaller than the extent of my kernel that I'm moving over my lattice to find a magnetization field. So this is a region of size much bigger than A. But also much smaller than a system size. Otherwise, we don't do statistical physics anymore. And so if you do this, then we arrive at a magnetization that is a smooth function of X. That also means that all of a sudden our magnetization is takes on values in between -1 and +1, right? So it is a continuous variable in its values as well. Any real value. So not just plus. So for example, if I look at an Hamiltonian term like H sum over I, then I can write this as with just this definition above. Oops.
when this prefactor is normalized to 1. And then for the paramagnet, you know, this would be give me a function b of, sorry, my brackets here. Sorry, a function b times magnetization. And then just sort of to give you an idea, without going into details, in general, I can then determine also the weights of any magnetization field as a function of x, formally by evaluating the number of states with this specific magnetization. In the very basic definition of the partition function. So this is just to show that in principle a bottom-up approach is doable. But the cool new thing to learn here is now the top-down approach. And that's the phenomenological approach to determine now this weight factor. Okay. And so how we do this is like we define the weight as by an effective Hamiltonian. So we say, okay, so there is an effective Hamiltonian, and if I take the logarithm of it, this is actually defining my weight here. And now I construct H with the following principles that I know about my system. Okay, so what we assume is principles that we look at is, for example, locality and uniformity. Which means that I assume in my spin system that the dynamics that all spins are the same, and there's no explicit dependence on the spin at lattice size 5, but it's I can describe this as a uniform property that there's a magnetization in the field in the system. So the system consists of and that these parts are in principle independent, but have the same interaction among each other. And consist of independent paths such that the overall probability is a product of the individual
of independent So that means that I assume I can write this Hamiltonian as a integral sum here, integral, because we have a continuous variable, as a integral over a function, a functional that describes the states of an individual in respective of where it's located. And we're running out of Greek letters, that's why we're losing a phi again. So that depends on the magnetization, which depends on X and may also depends on the spatial position. But I can write the same functional for all spins. Which says that the contribution from each dependent part X. So we can think about this as an energy density. Quality. And then to distinguish, if I have a uniform material, then there should not be a dependence on X. As I said, I don't care about the properties of the spin at site 5 nor the spin at 550. They are the same. It's that they have the same properties. So there shouldn't be an explicit dependence on space, but the magnetization obviously has a spatial component because I can have long range. Really think about these phonons. I can have long range collective motions. No dependence of phi on X explicitly. It's all positions are equivalent. Yeah, let me just quickly finish. And in a counterexample, example would be, for example, to have an external potential that is not uniform. So this is like an assumption that we're making here, but you have to revisit if you have a different system that you want to set up a field theory for, if this is really what you have, right? And think about continuum mechanics. You have materials that they have a homogeneous elastic property, but you can also have materials where I don't know, you glue together two different materials and their elastic properties depend on the spatial position, right? So this is something that you need to revisit. Yes.
Is there a difference between homogeneity and uniform material? Or
No,
is it just
it's the same.
okay.
For me, it's the same. It could be. Oh, and I should know this. So what? So if I go back to the elastic system, you could also have a system being the same. Let me use the same, having the same elastic modulus, but reacting different if stressed in this direction, nor in this direction, right? So you can in principle have different response into different spatial directions of a system. And this is either, can anyone help me out?
That's
So
isotropy, right?
this is isotropic. Okay, so isotropic, this is isotropy. That's on x, and then I would here put under symmetries, homogeneous, uniform. Yeah, no, I think, you know, you don't assume anything about isotropy when you use uniform, right? Do you? Ah, gosh. Okay, so you have to be like, that's why math is so beautiful, because you don't have to figure out the definitions of different terms. Let's just leave it open here, but in principle, yeah, you should think about, like, you know, that what you imply with saying uniform, right? It's not as well defined as a term like entropy in physics. So you need to put it down in equations so that you don't run into miscommunication. Okay, so here, as I said, like you could have in principle dependence on X as soon as you have, like, you know, electric field ramping up over your system or so on. But say we have a uniform material, then this would state that our beta H is then has no explicit dependence on the spatial position, and so it's just a function of the magnetization. But wait, okay, so now we just wrote down that, you know, our energy density only depends on the magnetization itself, but the magnetization is a local property averaged over a certain amount of spins. But I mean, the whole purpose why we're doing advanced statistical physics is because we know that the system is interacting, right? We know that the spins are interacting with their neighbors. And so if we just only confine ourselves to this local property, we may throw away these interactions. And so how can we actually functionally represent interactions? So these interactions mean that spin at one position is interacting with the spin at the other position. So that means that there might be, I can represent the spatial nature of these interactions with gradients on the magnetization. So in principle, my functional could depend on gradients of or divergences, to be correct, of this magnetization. So we do have interactions between different parts of the system. And so we should generalize actually that our beta H still has no explicit dependence on X, but we explicitly state that there should be these terms allowed. And this is to account for non-local interactions by including many derivatives. And I can go higher and higher. The next principle to consider is analyticity and polynomial expansions. And this is to say that what we do when we look at lots of spins that we are averaging over, we have kind of in mind this central limit theory. And if I have the system that's fluctuating, but I'm averaging over many variables, I can actually really describe the system nicely by its average, and so this allows me to also describe then the whole system just as a function of these averages, and taking into account long-range interactions, and I can really expand the system just as a polynomial of these functional contributions and various compositions of all of them. But I limit myself to those. So the idea is the field M is averaging over many spins analogous to the central limit theorem. Where the sum independent random variables approaches a simple Gaussian distribution. Also, in a similar fashion, we here think that any non-analytic analyticities that might be associated with spins are actually averaged out, because we're averaging over over enough spins. And so this allows that we now get rid of any non-analyticities. We know that we have an analytic functions, and thus we can expand this function of phi in powers of m and its gradients. And last but not least, the most important building block is to look at the different symmetries of the system that I have, because the symmetries survive this averaging process and really constrain the nature of the terms of my Hamiltonian. So, for example, rotational symmetry, and for those of you who took continuous mechanics or are sort of trying to take it in parallel, here you find it too, that rotational symmetry is a strong way to find how to set up the field theory for elastic bodies. And so what it means is that in the absence for spin systems now of an external field, which would be breaking this rotational symmetry, my Hamiltonian as a function, if I think of this magnetization, and if I say rotated by a matrix, which I'm indicating with these two dashed lines, this Hamiltonian should be exactly the same as the one of just looking at the magnetization, because it shouldn't matter from which direction I'm evaluating the system. So here are being an n-dimensional rotation. And so what this means is that since m is vector, and if I rotate a vector, I have different contributions in different directions. I have a problem if I have a linear component of the magnetization actually in my Hamiltonian. And so but how I can rescue that is if I have squares of my magnetizations, because then if I rotate them both, since a rotation is an orthogonal transformation, have a unity vector popping up in the Hamiltonian. The Hamiltonian stays untouched. So that means that no linear M term, and the first expansion term is thus the M square, which I can write as M x x and or individually as the sum over. This is just to introduce notation, because notation gonna get more involved, but not today. And so like this is the first term, but obviously I can also assume higher order terms of the nature of m to the 4, which would be nothing else but m squared and or other, as long as they're even exponents, you know, I can go up. So this is the cliffhanger for today, because we're like just 15 minutes away for writing down the Landau-Ginzburg Hamiltonian for the Ising model. But so you have something to look forward for Tuesday. And so we close for today. Thank you for your attention.